just over 60 years, humanity went from barely leaving Earth to observing galaxies formed billions of years ago. Look up at the night sky. For nearly all of human history, that simple act was the beginning and end of our connection to the cosmos. The universe was a collection of distant, untouchable lights. We saw them only through the thick, shimmering veil of our atmosphere. This air, so vital for our survival, also acted as a filter, blocking out vast swathes of information carried by light. The electromagnetic spectrum with atmosphere blocking most wavelengths visible and radio passed through. It was like trying to understand a symphony while only being able to hear the violins. You would get a piece of the music, but the full, rich composition would remain a mystery. In the next few moments, we will explore how we learn to hear the whole orchestra. What we call light is just one small part of a much larger spectrum of energy. Our eyes are tuned to a narrow band of this spectrum, the part we call visible light. But the universe is communicating in many other languages of light, like X-rays, gamma rays, ultraviolet, infrared. Our atmosphere is opaque to most of these, effectively blinding us to the most violent and the most ancient events in the cosmos. Supernova explosion, black hole merger, first galaxies, cosmic dawn render. To truly understand the universe, we had to find a way to get above the air. The space age began as a quiet revolution. We built new eyes and set them in space, reshaping what we know. It started with a practical question: how to lift machines above the air? The answer was the rocket, refined by centuries of experimentation. A rocket channels controlled explosions into immense, directed thrust. Pushing against its exhaust, it climbs against Earth's relentless gravity. The mathematics are exacting, the margins are unforgiving. Every kilogram demands precise thrust and precious fuel. Mastering this physics turned dreams into solvable engineering. The revolution did not arrive with starships, but with a faint repeating beep, a simple signal that circled the world. In 1957, Sputnik, a polished metal sphere, reached orbit. It was essentially a radio in a can, circling Earth every 96 minutes. Many saw geopolitics, science saw a profound proof. We could place an object into stable orbit demonstrated. That beeping ball proved we were no longer earthbound. It vindicated decades of theory and hard work. The payload behaved exactly as physics predicted. After the robots came the humans. The next great leap was not just to observe space, but to exist within it. This presented a challenge of a completely different order of magnitude. A machine can be hardened against radiation and vacuum, but a human body is a fragile biological system. Sending a person to the moon required solving thousands of interconnected problems. It demanded new forms of navigation, life support systems that could function for days in zero gravity, spacecraft capable of leaving Earth, traveling 250,000 miles on another world, and returning safely. It was the most complex technological undertaking in human history. The computers that guided the spacecraft had less processing power than a modern smartphone, yet they performed their tasks flawlessly. Astronauts learned to perform complex orbital rendezvous and docking maneuvers, a delicate ballet of celestial mechanics where the slightest error could have catastrophic consequences. The lunar lander itself was a spider-like machine designed for a single purpose: to descend to the moon's surface and land gently in a world with no air, with 1/6 of Earth's gravity. The success of the Apollo 11 landing in 1969 was a testament to the power of a shared goal. When Neil Armstrong and Buzz Aldrin stepped onto the lunar surface, humanity crossed an invisible, profound threshold. We were no longer just observers of the cosmos, we were participants. We could walk on the soil of another world, feel its texture under our boots, collect samples with our own hands. The treasure brought back from the moon was not gold, not jewels, but 382 kilograms of grey rock and dust. To the untrained eye, these rocks looked unremarkable, not much different from volcanic rocks on Earth. But in the pristine laboratories where they were studied, they began to tell a story. Scientists analyzed their chemical composition, their mineral structure, and their age. One of the most important clues was hidden inside the atoms themselves. They looked at the different types of oxygen, known as isotopes, locked within the lunar minerals. The analysis revealed that the ratio of oxygen isotopes in the moon rocks was almost identical to rocks from Earth's mantle. Rocks from Mars and meteorites that have fallen to Earth have very different signatures. The fact that Earth and Moon were chemical twins in this way strongly suggested a common origin. The leading theory, the giant impact hypothesis, proposes that about 4.5 billion years ago, a Mars-sized protoplanet named Theia collided with the young Earth. The impact vaporized vast rock, a superheated cloud, was thrown into orbit. Over thousands of years, gravity pulled this debris together to form the moon. This explains why the moon is mantle-like and why it has a very small iron core. The lunar rocks provided the hard evidence to discard old ideas and build a robust theory grounded in chemistry. Living in space for long periods of time introduces a subtle but powerful change: the near absence of weight. Astronauts in orbit are not weightless because gravity has vanished at ISS altitude. It is still about 90% of surface gravity. Instead, they are in a constant state of freefall, perpetually falling around the Earth. This environment, known as microgravity, has profound effects on the human body. Understanding these changes has become a major field of space medicine. One of the most significant effects is on the bones and muscles. On Earth, our skeletons and muscles constantly work against gravity. This stress signals the body to maintain bone density and muscle mass. In microgravity, this signal is lost. Bones can lose minerals at about 1 to 2% per month, an accelerated analog of osteoporosis. Large muscles in the legs and back begin to atrophy from lack of use. To counteract this, astronauts exercise about 2 hours a day, using treadmills with harnesses and resistance machines that create artificial loads. Careful diet and nutritional monitoring support the regimen, allowing crews to spend 6 months or more in orbit and return in relatively good health. But here is the quiet connection. Space bone research informs osteoporosis on Earth, helping millions, especially the elderly. By studying rapid changes in healthy astronauts, scientists test potential new therapies and exercise regimens. Lessons from long-duration missions directly improve quality of life here at home. The challenges of space offer a unique lens to understand our biology and to help those back home. While human spaceflight captures imagination, much of the scientific revolution has been carried out by a tireless army of robots. These explorers are our proxies, venturing to places too distant, too dangerous, or too long for humans. They are our eyes, our hands, and our chemical laboratories. From the sun-scorched surface of Mercury to the icy plains of Pluto, probes have charted our neighborhood. Consider the rovers on Mars: Spirit, Opportunity, Curiosity, Perseverance landing in chosen sites, then methodically driving across the landscape. With cameras across wavelengths, drills, lasers, and spectrometers, they analyze rocks in place. They send a steady stream of data and images from a world that may have once harbored life. A command can take 20 minutes to arrive. They cannot be driven in real time. Engineers send daily sequences. The rovers navigate autonomously around hazards. Small drives add up to kilometers, revealing Mars's geologic history, one rock at a time. Orbiters like Cassini and Juno map fields, rings, and moons. Voyagers now sail interstellar space, still sending data. The search for life, astrobiology, is now methodical and data-driven. We seek biosignatures, subtle chemical and environmental traces, most likely from microbes. Strategy: follow the water. Mars once warmer and wetter. Orbiters map deltas, rovers find water-formed minerals and complex organics. Fleeting methane teases us. This leads to something even stranger: icy moons with global oceans heated by tides. Cassini found water, salts, and simple organics in Encel-Udus's plumes. These are among the most promising places to search within our solar system. Because light has a finite speed, looking out into space is looking back in time. Sunlight takes 8 minutes to reach us. Alpha Centauri's light takes over 4 years. Andromeda's light is 2.5 million years old, when early human ancestors first walked the Earth. Space telescopes free us from atmospheric blur and filter, letting ancient light arrive with astonishing clarity. In 1995, Hubble stared at a tiny empty patch for 10 days. That darkness held over 3,000 galaxies. Because the universe expands, distant light is stretched into infrared. Webb is built to catch that. Its deep fields reveal galaxies shining more than 13 billion years ago. We can directly observe the universe in its infancy. We watch galaxies evolve and merge to form larger structures like our own. We study how the first stars ignited and seeded the elements for planets and life. We are no longer just guessing. We are watching the story unfold, frame by frame, across cosmic time. A privilege of our generation, made possible by a quiet journey into space. Perhaps the most unexpected discovery was a new perspective on our own home. We saw a fragile blue marble, finite and alone. That single image helped spark the modern environmental movement. Today, a fleet of satellites continuously monitors our planet's health. They track sea level, ice loss, and deforestation with precise global continuous data. This evidence underpins better models and future predictions. Satellites also guide navigation, broadcast communications, and connect remote communities. They warn of storms and help farmers monitor crops and manage water. In quiet ways, our work in space is woven into modern life, making it safer and more connected. We have gained a new story of our origins, written in moon rocks and the ancient light of distant galaxies. But most of all, we have gained perspective. We are part of a grand cosmic story, still unfolding. The light you see from the stars tonight carries a small piece of that story. We have only just begun to learn how to read it. If this changed how you think, follow and subscribe for more mind-blowing science by Dr. SK.